Welcome to Ask and Learn.
So we have a configuration of capacitors that looks like this. We have 4 of them in a circuit. And this one is 3, this one is 6. They're all in microfarads. This one is 2, and this is 4, so those are the capacitances. So I can combine the top branch and the bottom branch in series and then add the 2 up to get the total equivalent capacitance. So the top branch, we have when capacitors are combined in series, we have 3 times 6 and then divide by 3 plus 6. And that gives us 2 microfarads. And then for the bottom branch, we have 2 times 4 divided by 2 plus 4, which is 1.33 microfarads. So now we have something that looks like this with one capacitor on the top. This is 2, and this is 1.33. And to find the equivalent capacitance now, we add the 2 up, so 2 plus 1.33, which is 3.33 microfarads. We also have a battery that's 90 volts. And to find the total energy in this in the circuit, you take 1/2 CV squared, and this is the equivalent capacitance. So that's going to be 1/2 times 3.33, which is rounded, times 90 squared, which comes out to 1.35 times 10 to the minus 2, or 13.5 millijoules. This is joules. Now, to find the energy in each individual capacitor, well, the important thing I know here is that the voltage on the top and bottom branch of this circuit is the same. So then I don't have to worry about voltages, and I can just calculate the energy in terms of charge and capacitance. I also know that the charge through each of these pairs of capacitors on the top and bottom is going to be the same through the individual one in each pair. It doesn't matter because we have the same current going through them. So I can use this bottom circuit to say that the charge, let me label these actually. This will be C1, C2, C3, and C4. So the charge on 1 is going to be the same as the charge on 2, and it's just this. So that's going to be, we have the capacitance times the voltage. And like I said, the voltage is going to be the same through either branch. So the voltage is always 90. And the capacitance, I'm using the combined capacitance. So that comes out to 2 microfarads times 90 volts, which is 180 microcoulombs. And we can do the same for the bottom branch. Q3 is the same as Q4, which is C times V, and the capacitance this time is 1.33 microfarads times 90 volts. So this is 120 microcoulombs. Okay, now we can calculate the energy for each individual capacitor. So we have 3, 6, 2, and 4. So the energy through the first one, well, instead of using 1/2 CV squared, I'm going to use 1/2 Q squared over C. That way I'm just calculating everything with charge and capacitance. And then this is going to be Q1 and C1. Ooh, C1. So that's 1/2 times 180 microcoulombs squared over 3 microfarads. So this comes out to 5.4 times 10 to the minus 3 joules. For the second one, we have 1/2 Q2 squared over C2. So that's 6. Nope, that's the bottom. Still 180 microcoulombs squared. Now we have 6 microfarads. And this is going to be half as much, so 2.7 times 10 to the minus 3 joules. Now, the third one is 1/2 Q3 squared over C3. And Q3 is now 120 microcoulombs, because we're on the bottom branch now. And C3 is 2 microfarads. So this is 3.6 times 10 to the minus 3 joules. And then the last one, U4, is going to be 1/2 Q4 squared over C4, which is 1/2 times 120 microcoulombs squared over 4 microfarads. And this is, again, half as much, so 1.8 times 10 to the minus 3 joules. Now if we take all 4 of these, U1, U2, U3, and U4, that's going to be, let's see, we have 5.4, 2.7, 3.6, and 1.8. We add those up, we get 13.5 times 10 to the minus 3, which is 1.35 times 10 to the minus 2, which is the same exact answer as what we got when we did the total energy. So if you add up all the energies and the individual capacitors, you'll get the total energy.